Hey, welcome back to Math with Patrick and Quill. Today is April 10th, and we have problem number 100 from this Daily Epsilon calendar to solve. It's 100 days so far this year and 100 problems. Well, 99 problems solved because I have yet to solve this one. The answer is today's date, and we need to find how many of the roots of this expression here are non-real complex numbers. A lot of vocab today. So I'm going to call this expression right here a polynomial. A polynomial is some kind of like math structure, I guess, that involves some numbers, some exponents, and maybe some adding and subtracting between them. And so, for example, this is a polynomial, but if I do something like this, it's no longer a polynomial. So there's some rules that you have to follow. And a root of a polynomial is going to be some number that I plug in right here for x, such that I get the value 0. So to rephrase this question, how many roots of this expression are blah, 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 I'm basically asking how many different numbers can I plug in that produce a 0 that satisfy whatever condition is right here. I'm trying to find roots that are non-real complex numbers. This right here kind of seems a little bit repetitive to me. Saying something that is non-real just means that it's not a number between negative infinity and infinity. And maybe you're thinking, well, isn't that all the numbers? Well, there's more number systems out there, and we're going to talk about the complex numbers today. Let's hold off on that for a sec, though. Let's try to find some roots of this polynomial. Let's find some numbers that cause this side to be equal to 0. So I could do a little bit of algebra. Why not? Let's add 4,096 to both sides. And then now I'm basically finding some number out there. If I multiply it to itself 12 times over, it gives me 4,096. There really isn't like a good way to do this besides just like trying it out. I noticed that this is a very large power of 2, so I might be able to prove by listing out all the powers of 2 that I've memorized that this is actually just 2 to the 12th. I can go 4, 8, 16, 32, 64, 128. Actually, let me put that 128 here, because then hopefully all my numbers will line up in a nice little rectangle. There's 256, 512, 1024, 2048. There's a game a few years ago. I mean, it still exists, but it's popular, at least for me, a few years ago, that was called 2048. And so if you're counting by your powers of 2 and you reach this number, you're on the right track. And then finally, if we multiply that by 2 one more time, we get 4,096. So if you notice, it took me 12 steps to get here. And so this number on the right side is just 2 to the power of 12. And to me, that's enough to show that x could be 2 today. Now, that is a real number because, again, it fits that description of between negative infinity to positive infinity. And so I'll denote that by just saying 2 is an element of the real numbers, or it's in the set of real numbers. And so this one doesn't count for our count of 10 complex numbers. Again, I'm getting there. Another real number that would work in this equation is negative 2. So let me also write that here, because you could imagine if we multiply negative 2 to itself over and over and over again, we're going to get, well, negative 2, positive 4, negative 8, positive 16. And then this pattern would just continue as we keep multiplying by more and more negative numbers. And so once I reach 4,096, it'll be positive again. And so negative 2 also would work just fine in this equation right here. Negative 2 also is a number between negative infinity and infinity. And so negative 2 is an element of the real numbers. It does not count toward this 10 complex roots that I have. And I'm going to claim here that these are the only two real number solutions out there. Just to confirm this, I want to hop on over to Desmos and graph it, and then we can also see where this -2 and 2 show up. So I'll write it as a function here, x to the power of 12 minus 4096, and it really just looks like two vertical lines, but if I zoom out a certain way, let's go maybe -5000 to, I don't know, 10, you can see that it does have some kind of curve to it, and if I plug in a 2, I'm going to get a 0, and if I plug in a -2, I'll also get a 0. The problem today suggests that there are 10 complex roots to this polynomial. And as far as I can tell from graphing it, I can't see any other spot anywhere here where I'm going to get the number 0. And so that confirms my first idea of we have two real roots and only two real roots. And then we can't really use graphing to answer the rest of this question today, as in like to confirm where are those 10 complex roots and what are those 10 complex roots. Referencing something called the fundamental theorem of algebra is actually enough to just solve the problem outright. And so let's do that first, because that's the most efficient way to confirm that the answer is 10 today. The fundamental theorem of algebra states that the degree of your polynomial is the same amount of complex roots you're going to have. Or in other words, for this specific problem here, the degree here is 12. That's the highest power of any of my terms. And that 12 is going to be the exact same amount of roots that I'm going to have for this equation, or the same amount of numbers that I could plug in here to get a 0 out of this whole thing. So I can say here that the fundamental theorem of algebra states that we have 12 roots. And when it says 12 complex roots, let me get into it now. A complex number is one that has a real part and then an imaginary part. This real part is like the same two that you and I know, it's just the number. And then this imaginary part has this I, this number I attached to it. And the number I behaves in a kind of weird way. You can define it as the square root of -1. You could also say that I times I is equal to -1. These two statements are the exact same thing. If you try any real number to satisfy this equation, it's not going to work. Because say if you plug in like a positive number, 1 times 1, well, you're going to get 1. If you try plugging in a negative number, -1 times -1, that's still positive. There's no real number where when you square it, you get something negative. And that kind of justifies the existence of this number. It's really weird because no other real number does it, but this is a feature that mathematicians wanted out of a number. And so it's just called I, and when you multiply it to itself, you get -1. No other real number has that feature. And when we're talking about complex numbers, those are ones that have a real part and an imaginary part. Sometimes those parts just are 0, and so technically 2 is considered to be a complex number. Just because it doesn't have an imaginary component doesn't mean it's not complex. It's also a real number. It's also an integer. There's a lot of different ways you can classify numbers. So anyways, back to that fundamental theorem of algebra. It states that we have 12 complex roots. And I found 2 of them already. Those are these ones right here. And we have 2 real roots that I found here. That's the 2 and the -2. And I didn't find any more because you can graph this polynomial and you can see that you have 2 x-intercepts. And that's enough of a reason for me, at least, to say that, yep, I have 2 real roots and no more. Well, the fundamental theorem of algebra states that we have 12 total, and I only found 2 of them. So the other 10 are going to be complex, and they won't just have that real part. So the other 10 are complex with some kind of imaginary component with that like number I with an imaginary component. And that's it. We don't have to actually figure out what those 10 roots are to answer this question. By finding the 2 real roots and showing that there's no more, and by knowing that there's 12 total, I can say with complete certainty that 10 are going to be complex numbers, and they're going to be, oh, okay. Earlier, I was like, oh, why does it say non-real? Same idea that saying, 2 is a complex number. This is 2 is an element of the complex numbers. Just because it has, no imaginary part, you could still classify it as a complex number, but this is also a real number. So that's why it says non-real complex numbers, because it really wants those that do have this extra imaginary component tacked onto the side. So that's basically it. You find your 2 real roots. You prove with the fundamental theorem of algebra that there's 12 total, and that means there's 10 non-real complex roots left. We're done. Though I do recommend that you stick around, because it's kind of worthwhile and kind of interesting to figure out what these 10 complex roots are. One way to figure out is by factoring. We could factor this polynomial. I know that I have a difference of squares right here, and that's going to be the first way that I factor it. If I square root the first and square root the second, I guess that'll just be, 2 to the 6th, whatever that is. And then I kind of have this setup here where I have a plus on one side and a minus on the other. I know that this is a completely valid way to factor my expression. I have yet another difference of cubes. Difference of squares. I mean, technically it's also difference of cubes, but I'll see the difference of squares first. And I could convert that into x cubed minus 2 cubed times x cubed plus 2 cubed. And so I'm getting these 2 new factors from this difference of squares right here. Also, I know that I can factor differences and sums of cubes. So this first one I'm going to keep the same. And actually 2 to the 6th is just 64. So let's just do that. Then I'm going to have, how do I factor a difference of cubes? I think I'll have an x minus 2 here. And then an x squared. I always forget what the signs are supposed to be. A student actually taught me the acronym SOAP, I believe, where here we're going to have the same sign. This one's opposite, and then this one's always positive. That's same, opposite, always positive. And that can help you factor both differences and sums of cubes. So I'm going to have the same sign, and then I'm going to have the opposite sign, and then I'm going to have that always positive right here. Okay, cool. If you decided to do the whole distribution here, you would get right back to this where we started. So let me just color code this. This factor turns into this one, and then this factor turns into this one. And the reason why I'm factoring is that it's a really useful strategy to find roots or to find values that cause the whole thing to be 0. Because here you might notice that if I plug in that x equals 2 that I found earlier, it'll cause this factor to be 0. And if I do 0 times anything, it doesn't even matter what the other ones are, I'll get 0. So the same thing is happening right here, where if I plug in a negative 2, I'm going to produce a 0 in that factor right here. And then 0 times whatever else the other ones are, it's going to be 0. I can zoom in on these trinomials. There's supposed to be a square right here. These ones are quadratic expressions, and I could just do the quadratic formula on both of these. I'm going to get x equals negative b plus or minus a square root of b squared minus 4ac. That's supposed to be a 16. It's the 4 times the 4. All over 2a. And after following through with this quadratic formula, I'll find, I believe, 4 complex roots. And I'll get some kind of solution, an actual number to look at, instead of just claiming that I have 10 complex roots and I don't know what they are. It'll be really nice to actually figure out what these complex roots are. This 4 minus 16 simplifies to a root negative 12. Again, with real numbers, you just can't find any that multiplied, like the same real number multiplied to itself will never produce a negative. So we need imaginary numbers to help us out here. I believe this one will simplify to 2i root 3, because if I multiply 2i root 3 to itself, I'm hoping I get back to that negative 12. I'll get a 4 out of these, I'll get a 3 out of these, and then again, I squared is going to be negative 1. And so yeah, I do get a negative 12 when I square 2i root 3. So I'll rewrite the fraction like this, plus or minus 2i root 3 over 2. And then it's the exact same square root over here, so I'll just do another 2i root 3 over 2. And then we have two solutions here and two solutions here. And actually, let me simplify them just a touch. X could be equal to, well, why not? I'll actually write it like this, plus or minus 1 plus or minus I root 3. Because this could be a 1 plus I root 3, or maybe it's like a negative over here. And so this is just me being like a little bit silly, but a little bit concise to say that I have 4 complex roots by using the quadratic equation on these quadratic factors here. So I'll write that 4 complex roots. Where are the other 6? Because I had 10, and it looks like they're hiding in here. So just like I said with that fundamental theorem of algebra, the degree of your polynomial is going to be exactly the same as the number of roots you have for it. So if my degree is 6, I'm expecting 6 complex roots out of this factor. And so let me try it out. When is x to the 6th plus 64 equal to 0? Well, that's when x to the 6th gives us negative 64. And here, I'm just trying to find 6 complex numbers that produce the number negative 64. Fortunately, I know that like 2 to the 6th is 64. And I feel like if I just tack on an I on it, like the number I, I'll find one of them. So let me try that. I'll write that in orange. I guess orange is my color for complex numbers today. If x equals 2i, then x to the 6th is equal to 2i to the 6th. And then just using standard exponent rules here, it's the same as 2 to the 6th times I to the 6th, which is 64 times I to the 6th. And then I think the best way for me to think about what's happening here with I to the 6th is to break it up into 3 I squareds. Each of those is equal to negative 1. And so you get 64 times negative 1 times negative 1 times negative 1. And ultimately that gets me to negative 64, which is exactly what I wanted to get right here. And I found another complex root, 2i. That also works. Well, I still need to find 5 more. And here's one last thing, or actually there's more than just one more thing here. Let's graph these complex roots on the complex plane, and it's going to make a nice pretty picture. Here is the origin. Here is our real number line. And then our imaginary number line goes vertically. This is just kind of by convention. And let's graph our real roots. We had positive 2, and we had negative 2. And then here, I just found this complex number 2i, which was another solution to this polynomial, another root rather to this polynomial. And I'm going to place it right here because just when you graph complex numbers, your real part tells you how much left or right you're going to go. And then your imaginary part tells you how much up or down you're going to go. And so this 2i tells me to go 2 units up. And I could graph all of these ones. This says I have a real part of 1 or -1, so that means I'll move left or right by 1 unit. And then an imaginary part of plus or minus I root 3. The square root of 3 is about like 1.7, so it's like a little bit closer to the 2 than the 1. And so I'm going to roughly sketch them here. That one feels a little too high. Let me lower that just a little bit. It's about the same. And then same thing going on here, where I'll have a real component of 1 or -1, and then the imaginary component is going to be about -1.7 here. And so I have these 4 solutions represented here visually on my complex plane. 1, 2, 3, 4, 5, 6, 7. So I have 7 roots so far. I still needed to find 5 more. And maybe you notice there's some symmetry happening in my diagram. And I'm going to claim that the other 5 roots are going to be here. So that's 1, 2, 3, 4, and then 5. And you know what? Let's use the power of maybe a calculator to double check this hunch. So I'm going to hop on over to Wolfram Alpha here. One of the complex numbers we already know to be a root for this polynomial is 1 plus I root 3. And so just checking, if I take this and raise it to the power of 12, I should get, cool, there's that 4096. Because again, in the big problem up top, we have x to the 12th. So this is our x to the 12th, which is 4096. Subtract the 4096 that was already there, we get 0. Cool. And it would be exactly the same if I subtracted this one. We're still going to get 4096. If that's a negative, it's still 4096. Cool. The other numbers that I put in the diagram they're in different spots. And one of them, the first one that I wrote, the first little x, is going to be root 3 plus I. That's because I went root 3 in the real direction and then 1 unit in the imaginary direction. And if I raise that to the power of 12, this online calculator is confirming my hunch that it is 4096. There were 4 other x's that I did. 3 of them were basically just playing around with the positive and negative signs. And here, either way, if they're both positive, both negative, or one's negative and one's positive, all of those, raising that to the power of 12, gives me 4096. And then the last one, I believe, is going to be negative 2i. That's the little x that I drew at the very bottom of the circle. Raising this to the power of 12 still gives 4096. Just to show you that, not all numbers raised to the power of 12 hit 4096. Here, you can take a random complex number, raise it to the power of 12, and you get something completely different. So all the little x's that I put do line up with actual roots for that polynomial. So let's hop on back to the whiteboard. The last concept I want to leave you off with is that complex number multiplication acts in a very predictable way. If you multiply 2 complex numbers together, and let's actually take this one and multiply it to itself, 2 things happen. Thing 1 is that its length right here, or magnitude or modulus, that's another word for just the length of this distance, it will multiply by the length of the other one. All of these have a length of 2. You could verify that with the Pythagorean theorem, or you could just kind of trust me that, well, we both know this distance is 2, and it's going to make a whole circle here. And so if I take this complex number and multiply it to itself, its length will be 2 times 2, or 4. So it's going to be about that long. The lengths multiply and the angles add. And here I'm trying to erase that small little bit. There we go. And so here the angle is going to be 30 degrees right now. And so when I square it or multiply it to itself, it'll be 30 degrees plus 30 degrees. And so I'm also going to be shifting over that final point to roughly here. Then if I felt like doing one more multiplication, again, by this same complex number here, so I'm going to do that one cubed right now, the lengths will multiply and the angles will add. And so I have a length of 2 and 4, and then so the resulting length or modulus will be 8. And then I had an angle of 30 and 60, and so those are going to add together and go right up to here. That's going to have a length of 8, and it's only in the imaginary direction, and so we're going to get 8i out of this. And so actually, just to kind of confirm this, let me do that back in Wolfram Alpha just to show you. That was the complex number it was root 3 plus I, and then I raised it to the power of 3, and then that got me 8i, and then so here it is right here. That's that 8i again. So if I take this x right here and I multiply it to itself 12 times over, or raise it to the power of 12, same thing happens. The lengths multiply, the angles add. And so when I do 12 of those multiplications, you kind of saw my cursor do one whole loop around the circle there. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rotations of 30 degrees, and I'm going to land on that real axis. And so I'm going to have a real number. And to figure out the length, it's going to be 2 times 2 times 2 times 2. And we've already established that 2 to the 12 is 4,096. And so any of these complex numbers, let's take this one right now, will land at 4,096, which will be way over there. And here, let's just double check with this angle. Again, with every multiplication of a complex number, you're going to go a fixed angle around the origin. And it looks like this first angle measurement is 1, 2, 3, 4 spots over. So when I square it, it'll be 1, 2, 3, 4 more spots over this way, and then doubled in length. 1, 2, 3, 4. So wow, actually, when I just cube this number, it turns into a real number. And then once I raise it to the power of 4, 5, and then 6, we'll be back on the real axis. 7, 8, 9, back on the real axis. And so any of these 12 points here, if you think about complex numbers in terms of these rotations and stretches, all 12 of these are going to get right back to that number 4,096. If you want to learn a little bit more on your own, this is called De Moivre's theorem. I think it's a French name. And this is, the main math concept that really says with, more certainty and more authority that you are allowed to do these rotations and multiplicative stretches in order to compute complex number multiplication quickly. So we found all 12 complex roots. We know 2 of them are purely real, and so 10 are going to have non-real components. And so the 10 orange little markings right here represent the 10 solutions. And those are the 10 that count up to this 10 right here. So we're all done. Thanks for coming along for this long episode. And I'll see you tomorrow for day 101. All right.